Cancer is an aggressive malignancy to humans and definitely one of the primary causes of death worldwide. The current advanced knowledge about cancer development highlights the complexity of the disease characterized by inter- and intra-tumor heterogeneity. Radiomics combined with artificial intelligence are a promising tool for a better characterization of tumor heterogeneities. However, radiomics features are more complex than standard measures, and several factors strongly influence the stability of their values. It's here where standard reference imaging objects are required to develop and validate such novel methods before translating them into the clinical routine. But can we create more real tumor models? 3D bioprinting provides the means to fabricate spatiotemporally varying in vitro models with a wide array of biomaterials, with a potential for rapid fabrication of software configurable heterogeneous 3D tissues. Our idea, initiated by Dr. Shyam Sundar, consists of taking a reference tumor model and using 3D printing to create a phantom with non-biological composition. Then, multimodal and multiparametric imaging will be used to evaluate the biophantom characteristics. Next, radiomics and artificial intelligence will be used to select multiparametric imaging features that accurately characterize the model. Finally, the biophantom will be used in a multi-center setup to evaluate and normalize variances across centers, with the ultimate goal of helping patients. It is time to take a step forward in molecular imaging. Are you ready to join? We wait for you at booth 1.
According to the statistics of University Hospital Leuven, every month 200 to 250 patients undergo brain tumor MRI examinations. Depending on the type of examination, scanning can take 10 minutes up to an hour. For brain tumor clinical trial, there is a standard protocol where a certain set of MRI sequences is needed to be acquired. However, in clinical practice, MRI data are less likely to be consistent. Technical issues, inaccurate patient positioning on the scanner, and image corruption are some of the many reasons which might result in missing MRI sequences. On the other hand, most of the machine learning or deep learning tools have been designed to work with a consistent set of MRI data. So, in case of missing data, these algorithms will fail. While rescheduling the scans seems to resolve this problem, it's not a cost-effective or time-efficient solution. Therefore, to address this issue, we developed an AI-based solution. By using the complete set of MRI data which are available during the training, we train a powerful model called teacher model and let this model guide the training of the student model, which uses a reduced set of MRI data. Therefore, the transferred knowledge from the teacher model will help to maximize the performance of the student model. So, the learning framework we have designed is able to effectively use the available MRI sequences to achieve their fullest potential. It only relies on one MRI sequences for inference, provides remarkable results to segment the different subregions of the tumor, and therefore increases the cost effectiveness of MR imaging. If you're curious to learn more about our method and see the results, please come join us in booth number 2.
Hello and welcome to the third pitch. My name is Jan Gra. I've been working for Philips Electronics and the University of Aachen in the last 3 years. And I'm going to pitch image reconstruction in positron emission tomography using kernels. And the task of image reconstruction really is to give us the best image. And the best image for me is quantitative, and it should have a high resolution and low noise levels. And those properties contradict each other in a way, because even modern iterative algorithms converge towards the most likely image, but they also induce a lot of noise in the images. And we can see this here. This is a reconstruction with a modern reconstruction algorithm after 5 iterations and after 40 iterations. And you can see the image is sharper here, but it's also noisier. And usually what we do is we filter those images using a Gaussian, and then we get this image. However, we might have filtered also a lesion here, and you could not see it as clear in this image as you could maybe here. And to avoid this problem, we introduced kernels, which are basically basis functions, data-driven from the PET image itself. So not PET MRI, so it's not coming in from the MRI part. The next pitch will be about PET MRI synergies, but here it's just from the PET data. And this has shown to be quite promising in previous papers. For example, here, where each of those images originated from just 2 seconds of acquiring PET data. So here you can see the left heart of the patient, and here you can also see the right heart. So you can really see the heartbeat in this PET image. And if you want to know more about kernel-less dynamic reconstructions, how to do it, and how to apply it in the clinic, feel free to join me at my booth.
Hola, my name is Alberto. I am a physicist working in medical images. I started in the field looking at the complexity of the brain, its composition and structure, trying to understand the mechanism of the psychiatric disease. Then I wanted to move to different challenges. You cannot say to a patient, could you stop moving your heart for a moment because we have to take some pictures, please? This is why, for my PhD project and this program, I decided to move forward to the study of the heart. And in particular, in this booth, I would like to show you the results of the integration of the information obtained with 2 different powerful techniques, positron emission tomography and cardiac magnetic resonance. Through some examples that I have been working on, I would like to show you how this synergy helps us to overcome some technical and clinical aspects. Looking forward to see you there. Ciao.
Hello everyone, I'm Shikai, a third-year PhD student who is doing my effort to contribute to a small step to the personalized medicine in the field of selective internal radionuclide therapy, in short SIRT, for liver cancer. So what is stopping the personalized treatment planning from entering SIRT? The traditional workflow requires a large amount of manual void delineations and can't integrate the information from multimodality images through good image registration. Therefore, the physicians prefer to use less quantified and less precise methods for dose calculation, which requires fewer image analysis techniques. Our project aims at bridging the image analysis techniques, including AI, with the clinical demands to provide the physicians with semi-automated solutions which segments voice and register multimodality images semi-automatically and requires as few as manual interventions. In this way, the physicians will have the opportunity to achieve a more personalized treatment without costing too much time on the manual workload. Currently, CN liver segmentations have been deployed in the clinical workflow for CT and MR images, even for those images with low contrast and severe artifacts. This frees the physicians from manual liver delineations while obtaining good quality contours. Besides, segmentation-guided registration for multimodality images is also going to be applied into clinic in the near future. For more information, you're welcome to join my booth in the booth session. Thank you for your listening.